Dr. Sun, are you able to hear us from the group?
Okay, good afternoon, everybody. So welcome to the next ICON seminar. So this week, we welcome our beloved Young-Jun son. He's James Stolberg Head and Ransberg Professor of the School of Industrial Engineering at Purdue. So he's a department editor of the Institute of Industrial and System Engineer Transactions, and served on the editorial board for 6 other international journals. And he got many awards, including the Outstanding Young ME Award and also the Best Paper Awards, many of them, right? And also the Best Paper of the Year Award. And he received many grants from NSF, Prof, US DOT, USDA, USDOE, and ISD, among others. So please join me to welcome Professor Son with the presentation today about multi-paradigm simulations and different models for planning and control. Thank you. Hey, thank you for having me here today. So I'm going to talk about multi-paradigm simulation. And in short, so I'm going to talk about some innovative ways of using simulation. I see a lot of the industrial engineer here, system engineer, and many other engineers, but I'm going to talk about innovative use. So for students, hopefully after presentation, this helps to solve some of the research topics directly or indirectly. And the faculty, I love collaboration. I'm looking for the collaborative, interdisciplinary type of the proposal. And I have actually invited some of our staff members with the Gateway Complex for this digital twin development and IoT and so on. Hopefully give you, some of the insights based on the work here. So multi-paradigm simulation. So simulation, I'm pretty sure that most of you do the simulation one way or the other. So how about computer simulation? So in industrial engineering field, at least there is a discrete event simulation. And then here, doing type of the model, you model like a service system like a McDonald's or like a factory product flow. And here, really top down, given a system, we look at everything top down, and then each individual entity's kind of capacity being driven by the process, okay? And then agent-based simulation is exactly the same, but you simulating the same system, instead of looking at from the top down, we look at from each individual, the entities really active and detailed, and so that's actually the agent-based simulation. And then we have a continuous time simulation that I don't know, many of you may be doing like a system dynamic model, which is like a difference equation or differential equations, or physics-based simulation. That's actually the it's also a lot of the differential equations for like the game engine. I don't know any of you play Unreal and Unity. So that's so the computer is simulation. How about the physical simulation? Today I'm going to talk a lot about, physical simulation, traditionally like even posting a coin and conduct a real experiment, or hardware in the loop simulation for the smart manufacturing control, human in the loop simulation, So simulation is really running in real time, interacting with the human and the machine. So these are the overview of the simulation, and I want to touch upon a little bit of the main things here. That's the 55 minutes. So I'm going to talk about these are all different paradigms, but we are doing exactly the same thing. Not Apple basis. We can actually mathematically prove that we are modeling exactly the same thing using different paradigms. So discrete event versus agent-based model. Well, this is the simplest possible queuing, MM1. Okay, exponential drive and the exponential service time. And then we have the C, so one server or C, multiple servers. And if industrial engineering student, if we ask to develop this model, it takes us 30 seconds. You just put one server, one queue, and then distribution of arrival and circuit. So that's all discrete event. And we can make as complex model as possible. It's a platform like Arena, Celio, many of the tools developed by many former Purdue professors and alumni. They are dominating the world of the discrete event simulation that are really complex. Right? So that's MM1. Well, you can still use the discrete event simulation to develop agent-based model. Instead of being a passive entity can be very active, very picky human behavior model. And this is Arena that our the student senior that in class we use discrete event simulation, but customer arrive. Okay, McDonald's, if the line is busy, by saying wait or after 2 minutes, by thinking about important hours or coming back. You can, again, this type of the model can be as detailed as this one if you want to employ agent-based model in discrete event simulation. Okay, that's all again, two different. Well, now as the system engineer, how can I describe this more active the behavior using like something like UML, state chart or finite state automata, state machine. So that's exactly agent-based model. Okay, if I want to spend 2 minutes to comparing about differential difference equation versus UML state chart agent-based model, we can mathematically prove that we are modeling exactly the same system equation. Okay, so on the left-hand side, and then the right-hand side is agent-based system. Left-hand side, the system dynamic model. I'm going to use this mobile phone today a lot, so I don't know what is the current version of the mobile phone, but as soon as the new iPhone comes out, there's always, this is a curve that there is nobody, number of the people who buy this new product, 0, and then at some point, many people, okay, buy it. And then, so this is a adopter, and this is the potential adopter of the new technology. It's very simple, very, very simple traditional product, the diffusion process that many is used as an example. So to develop this type of the simulation, this is a system dynamic model. And then, so this is really, we call it star flow, right? Star is, this is the number of the potential people continue to decrease. And then this is number of the adopters continue to increase. And then what this is the rate, how fast the people buy, so that depending on a lot of the advertisement, how many people put, the promotions and so on. So those are the system dynamic models to result in this graph. We are doing exactly the same thing on the right side. Here, people, 1,000 people, 10,000 people is liquid, right? Continuous variable. But we need to discretize this liquid into this individual agent. Okay, you can make it a million people. You can make it each individual, or depending on computation, you can make 100 people as one agent, 1,000 people as one agent. But we need to discretize. So that's the key. Once you discretize, this is the state. Okay, state chart. Everybody initially in the potential adopter state, and then at some point I buy the product. And then here, this is called a state transition. It can be event-based, it can be temporal-based every certain time. And then if you do this one, it actually it's not as smooth. So that if you increase the number of the agent, the graph will be smoother and smoother. And I'm gonna create mathematicians. We show this is a possible case. We can actually prove that how complex things we are resulting in exactly the same. So this can be simpler than this one, but there is a outgoing. It can be simpler than that, right? So the system equation is A is really initial A0 minus constant over time. Really, right? So that's as simple as possible. And then, so this is really, we solve differential equation. This is a system equation. How about what is its analogy? So here now, this is the state chart. This is again system dynamic. This is agent-based model, and each agent, well, the way how we look at it is, this is the time it takes that all the liquid becomes zero. So this is the, the graph. And in terms of each individual, throughout the time, the probability is uniformly distributed. The first agent, time to departure is this time departure. So the time, throughout the time, the departure from the state, leaving the state is equally distributed, uniformly distributed. So because of that, I just mentioned that A0 volume is a K agent. One agent is A0 over K volume. I just mentioned that each individual agent, it's a PDF. So the time to leave the state is uniformly distributed. PDF of this constant is a reciprocal, I guess, right? And then, so this one, and then we take the CDF of this one. Well, by CDF, the definition is any chance, any time that the people have, departure time is shorter than right now, which means all the agents who have left the state, right? So that's actually the probability. So you would take the.
Sorry, I'm just hiding the bar.
Okay,
at
okay.
One of the, maybe people wanted to see your awesome research, so I think.
Okay.
Our request, so I'm sorry.
No, okay.
Any experts?
I think under more, you are on the right hand side,
Right hand side,
under more,
under more.
then you should be able to say I slowly move.
It's muted?
No, it's not muted. I mean, you can.
Oh, okay. I see. Oh, that's the one.
Now gone.
Yeah, right there. That one. There you go.
Okay. Thank you. I learned something. So, okay, but anyway, so that's actually the probability. And then on next slide. Okay, next slide is, so this is what the probability. So this is really expected value out of the K agent multiplied by probability. So these are what? These are the number of the people who have the left. So what is the number of people who remains? K minus whatever the number of the people left. And if you calculate, this one will give A0 minus RT. So again, simplest possible case, you can solve the differential equation to get this equation, or you can use the expected value for the each individual one. You can result into the exactly, but you can do it for the the uncertain time, complex case, and all. So when I teach a PhD level course, we actually explicitly derive for the different complex case. We are modeling exactly the same thing. Of course, there is a limitation, right? The agent-based model can go as detailed as possible. System dynamic model has its limitation, but we are modeling exactly the same thing. Okay. So I think I mentioned enough about the discrete event simulation agent-based model, system dynamic model. Later, I'm going to talk a little bit about the game engine DA as well. So second topic is simulation-based planning and control involving discrete event simulation and hardware in the loop simulation. This happened to be, by the way, my dissertation. Okay, so the 23, so 20, I graduated 2000, 23 years ago, real-time simulation-based planning and shop floor control. At that time, we didn't call it digital twin. So this is a digital twin, by the way. I will show you
how simulation is a twin and drive the real system, which is smart manufacturing, robots and machines, conveyor belts, and so on, okay? Mobile robots. So that's my dissertation pensing. I will show you. Okay, I'm gonna use a two-system smart manufacturing. Second, we have Air Force, the project, right? They're using the UAVs and ground vehicle for the, I'm from Arizona, as you may know, right? The Arizona border, that we have a lot of project for the animal issues and some, illegal drug traffickers and so on. So that we needed to use this kind of the sensor system. So, okay, so this is the factory. We have a 30 times bigger factory now in Gateway Complex, but this is the facility that I played with. And then function-wise, it's not different. We have, autonomous CNC machines, CNC milling machines. We have, actually, I didn't have a picture, so I had a robot and cobot. Human can be part of this system. And then AMR, we are in the middle of getting a lot of autonomous mobile robots and then drones. So all this, the smart, connected, the manufacturing, the systems. And so this is a very busy slide, and this is paper you see 2002. I purposely put some of the early paper on digital twin, and that there is a lot of the model-based system engineering that is also very popular. I will talk about. Okay, so it's a very busy slide, but if you look at the left-hand side, nothing new here. This is a textbook simulation. Everybody use discrete event simulation to look at different scenarios, conduct a statistical analysis, and then identify some good solutions, right? So that's nothing new. But so this is a simulation, traditional simulation like a Arena, Simio, Automod, whichever that you use, right? So traditional textbook. And then here we do the rule. I needed to show you what specific rule that we talk about in real-time shop floor control. But so, one rule, second rule, and then a decision space can be very large. And a long time ago, we are using neural network actually to reduce the decision space. But I'm sure that there is a lot of the, again, good, the deep learning, actually, the people that can help to optimize this decision evaluation here. And then whatever these solutions, we do the statistical analysis, and then we identify best rule. Best rule is distributed agent. Each machine needed to solve its own problem. Each part, every part, because I can visit machine 1 and machine 2. So everybody make its own decision. So I can make a decision based on rule, based on policy or heuristic, right? So combination of the rules for each and every entities that constitute the decision space. Okay, so I will show you some examples. So that's a planning side, nothing new. And then right-hand side at that time was the novel, right? Using exactly the same simulation. It's not simulation anymore. Simulation start to generate message and then drive robots and machines and conveyor belts and so on. Exactly the same software. We just change the system variable. Okay, so that's actually right-hand side. But let me show you some of the decisions that we are addressing in the shop floor control. So in a shop, what type of the decision are we talking about? Traditional. It's a traditional, but still 97, 98% of the small to medium, still they do. Okay, you solve all this routing problem before factory. Whether it's 2 months ago, 1 week ago, okay? There is not much real-time decision, I noticed, right? So, but what is our goal? Smart factory, online decision, and based on real-time data, I mean, sensor network, IoT, nowadays, abundant, right, the data. And I keep hearing that they just get the data and they don't use actually much, right? So as I said, each machine, I can invite multiple parts. So I needed to select, we call it part selection problem. Each part, now I can visit machine 1, machine 2, machine 10, so that it's a machine selection problem. And then you can have a reliability problem. You can have a robot selection problem, many others, but I'm not going to go much detail than this one. In terms of the objective function, of course, traditionally, we want to minimize, we want to maximize, we want to, of course, we don't want to sacrifice the product quality. However, this is a DOE project in Arizona with one of the medium defense company. Okay, that energy, that's a real project, the DOE project. And then here, in addition to the traditional objective nowadays, this reducing energy bill is a huge, especially the state like Arizona. Let me show you what I mean by that. So this is a power meter. I'm pretty sure that we have energy experts. So this is a power meter. And then when you, so this is a typical CNC machining, right? That's the machine that we have in the gateway complex. This is the Y is a kilowatt. And then when you run your machine for the 15 hours, the same machine, one single machine, and then I actually magnify the 3 hours. If you look at it, even this is off, machine is on, the amount of the energy consumption can be what, 12, 3, 4 times, it can be different. And this particular company has 70 machines. In the middle of the July, August, they have 50 air conditioners. And then today, how many NC code or programming code do they have each industry? 1, which means whether we are busy, whether we are idle, whether August, whether it is January, they always use the same code, which means whether we are busy today or not, they always try to maximize their productivity. And then their energy bill will be, it'll be very, very, very high. Okay, so what we do here is, so I don't know, there is some program called the demand response program. That what that means is the price of the electricity is differ depending on the day of the time. Arizona, most of the small to medium company, they actually sign up. So the big problem is if, of course, they do not want to sacrifice productivity, but should I always use the machine that consumes the highest energy? No. If you are not very busy, I would pick the second machine or the third machine, so that the key here is you want to reduce something called the peak. Peak needs to be reduced so that energy can be, it's spread throughout the year, okay? So that's a very practical, i.e. production planning problem. That's a very, very important problem. So here is the decision, incorporating what I just mentioned, right? So this is my figure. So let's see whether it makes sense. We have 4 different parts. Each part has, I simply oversimplified, right? So this is a process plan. Again, 99% today, they don't have alternative. It's everything is not only linear, all the even program is already developed, the 1 month or they never change, right? But we want to make as many alternative decisions. We want to defer as late as possible, like real time. Well, in order to do that, then somebody needed to, select, remove, right? Linearize, remove a lot of alternative. But hopefully that our computers are getting smart so that all the decisions are made during the real time. Okay, that's actually the goal. So here, let's use a part 4 as an example. Part 4 looks like, based on the process plan, I can go to machine B or machine C. Here, this is the system. So machine part 4 was just done with the machine A. Based on my next process plan, I can go to machine B or machine C. But looks like right now both machines are occupied. So the decision is, should you just stay or should you move to the buffer? Okay, those are the kind of the rules that I'm talking about. If this is available, I can go there. If both of them are available, you need to have a rule, right? That, the one with the minimum energy, or I would go to the one who has, the less congestion in the future, whatever that the, heuristic you need to, add it. So that's actually one decision for the one machine, but you need to have that decision for the each and every machine. And then from the part perspective, part can go, right? The next part, I can go to the next machine. So which part are you going to? So that has a lot of the, the decisions for the parts as well as the machines. So that's actually the real-time decision I talk about. Now I want to spend some time on the right-hand side. I think Dong-Yang, you like actually this one. So this is a control. The left-hand side is nothing new, right? It's just the traditional use of the predictive analysis using simulation, nothing new. Right side, simulation that you saw here, that's exactly the same simulation. Really, it looked, we happen to use Arena, but we can use a Simio or anything, right? And then we just change the public variable so that this is not simulator any longer. It's not simulating. There is no event calendars and so on. What it does is it using TCP/IP, okay, TCP/IP, right? The network, so that when simulation says robot, you need to pick the part, instead of the simulating robot, a message is created using TCP/IP should be sent to the robot. And then I needed to wait until robot completes the task, come back, and then I send, since this simulation is we already developed this logic, right? So that exactly same logic is used to drive the real system, okay? So again, clockwise is not fast running. Simulation usually run very fast, but clock should be real time. 1 second in simulation is 1 second in real time. That's the first modification. Second, instead of the simulating, you need to generate tasks. Third, it should be exchanged with a real hardware. Okay, all this hardware using finite state automata, okay, or set theory, or UML state chart. There was an outstanding talk by system engineer, right? That a couple of weeks ago. That's exactly the model that we are talking about, right? And then so this is what the graph look like. This is a very, very, very simple system, right? One robot and one machine. And in a typical class, simulation class, if I ask a student to develop simulation of the one robot, one model, your model will look very aggregate like that, a few nodes. That's a aggregate, approximate model. If you want to do control, means you have a robot and you have a machine, you want robot put the part to the machine so that you need to be as detailed, otherwise robot will crash to the machines and so on, right? So how do we provide that kind of synchronization? This is that, in order to control robot and machine, these are the number of the state in the state chart. You know, what it does, what that means is, so this is a machine, this is a robot, right? So robot has nothing to do, has no idea about machine. Machine has no idea about robot, but supervisor needed to tell that machine, you open your hand. Again, machine has no idea about robot, but robot now, robot, why don't you put the part to the machine? You cannot just leave it immediately. You need to wait until machine crashes, and then you are allowed to leave. That's why this much, all the details synchronization needs to be specified using this type of the system modeling graph. And then this is a graph, like a unified modeling language state chart. This is the graph, and this is a formalism, set theoretic, you know, Weimarian theory, set theoretic model, but that's basically the same thing. And then my dissertation, by the way, was because of factory, today you have this layout, 5 machines. Tomorrow you can add another machine. Tomorrow you can change the layout. When you change, you develop this software simulation. These are all the C++ code in the distributed computing environment, to also hardware, serial port, parallel port. If you human develop it, it takes 3-4 months easily. And using model-driven architecture, I automated everything. So you just change it, click a button, all the simulation, automata, executable models, everything that runs in TCP/IP. So maybe it's not conceptual. Somebody said, oh, that's a concept. No, you click button, it is so also error-free. When people do all this distributed with messages, right? Everything is generated from the same model. And then that's actually model-driven architecture and the automatic code generations. Okay, so in summary, I'm gonna show very high level the cartoon. Okay, so this is Arena runs in real time. This is a somewhat simplified graph of the supervisor. This is a graph for the robot. This is a graph for the machine. We have a graph for the UAVs. we have a graph for the unmanned aerial vehicle. You need to develop this graph for each classes of the different resources, right? So robot, whether this robot is an ABB robot or IBM robot or Fanuc, okay, low-level program may be different, but behavior-wise, all the robot does is pick from somewhere, put to somewhere. That's it. You can pick from here to here, here to here, but in terms of the task, it only pick from put to. That's actually what it is, right? That's why we can develop system like this. But in this, again, it's not simulation anymore. As soon as I run it, it create the task, send it to the TCP/IP network. It's just sent to this can be PC or this can be any microprocessor that sits in front of the robot. And then a robot, when we receive it, physically you need to pick. And then for the simplification, I didn't include the completion. But in order to accomplish, this is a digital twin, right? I heard a lot about the digital twin in the conceptual level. Actually doing that, it involved a lot of work, right? So that's a two-way. One way was a command. Two-way was I'm done. So that simulation knows that, oh, robot is done. Then this one is very smart, right? So now I needed to ask door physically open. It can take 10 seconds. It can take 10 minutes, but this one needed to wait until okay message comes back. And then next one, ask robot, now you can put the part. Okay, this is the best animation that I can do. Okay, so and then you continue. Okay, that's my digital twin for the smart factory. Exactly same thing that can be applicable to our gateway complex. Now I'm going to talk about how we extended our project to a lot of the UAVs, UGVs, and so on. Okay, the director of our program manager, Dr. Tarima, was here actually a couple of weeks ago. So she became the director of AFOSR. But this is the result of the 6 years work of the AFOSR. And so we have 3 levels. The bottom, again, this looks like a desert. The bottom one is the surface. So the desert that we have, it's actually, it can be unmanned, but a lot of times manned, right? The real human actually drive the car. The second one is UAV. This is the project a long time ago that many people use a drone. Okay, long time ago. And then, so our first project, we only had 2 levels. And the second stage, we added a third one called the aerostat. So that's actually even higher. And then this aerostat actually doesn't move much. And then each level, we use a different type of the sensors. So the bottom one, we use some mobile one like guided vehicle or stationary one like a thermal sensor imaging or seismic, vibration sensors and so on. The second level is mostly camera. Okay, that we put the camera to the UAVs, and then third one is like a satellite. Okay, the kind of the radar. Second one actually the LiDAR and the radar, the images that we are using. And then this is exactly we extended our idea: simulation-based planning, simulation-based control. Here instead of the machines and robots and conveyor belt, we use the UAVs and UGVs and aerostats and so on. And then, but type of the simulation, since today, I try to focus a little bit more on the multi-paradigm simulation. We use both agent-based model as well as a physics-based simulation as part of the evaluating the decision. So I'm going to show you the first one. Okay, video, audio works. So this one is agent-based model. I'm sure that we have some agent-based modeler here. It's something called the RePest. That's the tool developed by Argonne National Lab, or you can use any logic, which is a commercial one. But this is a border, Arizona, the area. And then this is a hardware in the loop, just like robot and machines. And this is, Arizona, the UAVs and then ground vehicles. And that they're actually, again, still based on those state charts, right? So state chart. But here we have 20 simulated UAVs. We have 20 simulated UGVs, but each other, they do not know whether they are interacting with a real one or virtual one, because we are using exactly same sequence of the interface. So Air Force asked us to test the scalability of the system that we are testing. Still, we want to play with a real, so that we understand all the, the detail, the physics, dynamics, right? So this is okay. You need to pay a little bit attention to see what's real and what's simulated, right? So top part is a real one. So this is a park. This is real video, right? Park, our student. 6:30 in the morning as on Saturday, before not many people around in the park, right? So we did a lot of this kind of experiment. Now, right, a lot of the regulations, right? You run the UAVs, and so that's a little bit before that, right? So we had more freedom at that time. But anyway, this is a real scene of the park. This is what the UAV sees. The camera from the UAV sees of the people that entering the shelter area. This is the video that UGV sees. So we have a group of the UAV, group of the UGV. Bottom one is a Unity. Unity is a game engine. When I talk with the high schools, even nowadays, many high school students play with Unity, Unreal. That's a software that I use to develop program. When you go to the Disney World and Disneyland, that's exactly the same software, because the fidelity library of the mother asset gets better and better. So we should use, the more of this actual tools. And then, so what we do here is, the scenario that we look at here is, what about group of the people enter the shelter? Of course, UAV we cannot see, but we needed to put the UGV so that they are doing information fusion. Their goal is to maximize coverage of the crowd movement. Here is the crowd movement. I'm sure that there is a lot of expert in open, like CV here, right? No? Open CV. This is the vision, computer vision, that whether crowd is joining, whether crowd is splitting, some of them out of range, or each of them make a random movement. Okay, so I'm not showing the algorithm, okay, the optical flow algorithm. I'm sure that we have expert here, optical flow algorithms, or we have individual human detection. We use, HOG, histogram of oriented gradient algorithm to detect the individual humans. And then, so when we used it, again, people here. So this is a UAV view. And you see little guy here, that's a UGV. And this is what UGV is seeing here. These are people here, right? And then here on the right-hand side, what we do is the top part is, again, our goal is when people make a lot of different type of the movement, how can you use UAV, UGV to maximize the coverage of whether it is animals, or in this case, again, drug traffickers or so on, right? And then the top one is, the red is actually the good one. When you use both UAV, UGV information, always the coverage is higher than you use just the UAV alone. That makes a lot of sense, right? UAV, if it's a cloud or a tree, you cannot see that. UGV, ground vehicle, you cannot see that if there is a big rock in front of you. So we needed to fuse both actual information. So that's the second part. I'm gonna extend shop floor control to top floor, called supply chain. A lot of the project that we did with the Boeing commercial in Seattle. So
just one question.
Yes.
About the previous one. How scalable are they? Like, if they were very large, can they do delay asynchronous, this kind of thing?
yeah, that's a synchro. It's actually depending on how scalable, depending, right? That's why it's all about, if we have a single computer, even factory, if you can have a single computer does everything, 100 machine, that would be best, but that's not feasible, possible. So I'm going to talk about scalability actually here, but that's why you need to, that's actually one end. performance synchronization wise, having central kind of the computation control is the best. But how about that computer dies, right? That entire system dies. And also every machine, each machine, there is a little disturbance. So that if this computer communication is not perfect, I cannot react to the disturbance very fast. So that it's better we just distribute actually computation a little bit. And then real research is really hybrid, right? Instead of the pure hierarchical. Pure hierarchical is, again, I'm sure that we have developed a lot of algorithms, but each of us make decision, how does that contribute to the system level performance? That's always a challenge, right? That's why it needs to be the hybrid summary. But this one, you will see exactly we aggregate. The reason is the computation and also availability of the data as well. If your data is not available, you get fast enough, modeling going in detail, it's meaningless, right? Based on what, the data, right?
So when you have data, the example people, if you have more and they're collecting data will be delayed.
Exactly. Yep. So next one, actually, I have some, the scalability issue here. So extension to the top level here, this is really, you saw this picture. I mean, we use the simulation-based planning and control for the manufacturing system. If you look at right-hand side, this is a traditional supply chain or supply network. We have a number of the suppliers. We have a UPS or transportation network. We have an assembly plant, and then transportation network. We have a retailers or distribution centers or whichever, right? So these are, so what we did was exactly we extended digital twin-based control to the supply network. And to do that, we need to have an automata model, resource model, but I'm going to only show you simulation because today the focus is the simulation. And then, so there are two ways. One way, this is real Boeing commercial project, but one way you do is without aggregating, I just integrate, so supply chain, you have 1, 2, 3, 4, 5, 6, 7 facilities, assuming that each facility has its own simulator in different location. One way is I can construct a simulation integrating already existing discrete event simulation. That's one way that we did. The second one is that simulation may not be available. Also, it's a lot of so on. So that how about we aggregate? Still, system dynamic based planning is a lot more dynamic and detailed than just a mathematical, the programming alone, the decision, of course, right? So that's why it's not, it's still, it's not, very aggregate. So first one is like this. I want to show you a video. So you see the Arena, ProModel, Simio, any logic power sim that because when you work with the industry, each of them have their own legacy system. Our demo, we just tend to integrate all widely used software. But here, this is assembly plant, Arena. This is what the transporter UPS of the Arena. This is a ProModel, okay, of the supplier A, Arena for the supply B. For the demo purposes, I put 4 independently running simulator in one computer and we videotape. But in our Boeing project, of course, this one runs in Charleston, Carolina. This one runs in that was Boeing commercial, not Boeing defense, okay, that the Seattle area. This is the another. So what we did was we developed SOAP-based web services. And it looks actually simple, but in order to integrate, each of them has their own different simulation clock. So we needed to have a server that communicate with all 4 simulator, but this should be generic, whether you have 2 simulator, 4 simulator, 10 simulator, we allow them to, so time needs to be synchronized, right? We don't want this simulation is the tomorrow, this simulation is today. That's not good, right? So you needed to synchronize time, you needed to allow information exchanges, but many industry love this. Why? They form the supply chain, means they collaborate, but still they belong to different company so that they don't feel comfortable sharing proprietary data so that this technology allow You have a simulator, you have a simulator, let's simulate. And then I help to integrate, but you don't have to share the data each other. So that's actually one way, right? And then the second, oops. The second one is aggregation. So actually, let's only look at top part. Top part is system dynamic model. Do you remember stock flow diagram, incoming fluid? Everything is a fluid, right? Incoming rate, outgoing rate. System dynamic model is a lot more aggregate. It runs a lot faster. So 90% nowadays, when people develop supply chain, they develop model in one computer, right? So that's actually the using system dynamic model. But so Jayendran Venkateshwaran, the seminar speaker who came, IIT Bombay department, he was my first PhD student. His dissertation was in the first stage, we use this system dynamic model to develop good decision. Of course, your model is aggregate. Once you develop a good decision, optimum decision, we want to test its performance using very detailed simulation now, connecting all this distributed discrete event simulation. That's a two-way, right, that integrate the system dynamic and discrete event simulation. That was his dissertation, right? So, okay. So now, last one, human behavior. So I'm glad that Danny is here because we talked about the BDI, a couple of days ago. And as I said, I'm looking for the collaboration as well, right? So I want to show, many things. But so human behavior model, which is also used in our Air Force project. As I said, drug traffickers that we don't have much data, right? So we set up a lot of the simulation of they have a tendency to leave early in the morning, they hide, those type of things that we want to understand, right? So this is also a very busy slide, but so this is our behavior. That's a MURI project, Air Force MURI, that multidisciplinary, the research initiative project, okay, MURI project that we were part, right? And then, so this is the outcome of the project that I led. And then this is a human behavior model. So that's why I need to talk with the human, the factors, the expert actually here. But instead of using the tool like XR or SOAR tool, we decided to use or develop our own framework. That was good. Once we developed, there are many partners that they want to use it for the transportation project. We have people in a SUNY Buffalo that they want to use actually the King Hee and the Rajan Bata that they use this one for the hurricane evacuation. And then, but let me show you what type of the simulation that I'm talking about. This is the emergency evacuation simulation. So this is a Washington, D.C. mall, monument, July 4th, fireworks, 7,000 people. The scenario, by the way, I didn't develop, I'm given by government, okay? So this is a project with a scenario given by Homeland Security, NIST, and then I used the human behavior model from Air Force project, because they said I can use any scenario. At that time, I happened to have this emergency evacuation, the scenario. I combined both actually project. And then you see what happened is, so everybody was, and then this is instance, bombing attack, right? When bombing attack occurred, you may have noticed that everybody, the color was blue. Blue means their behavior was normal behavior. And then when incident occur, their color changed from the blue to pink means they have been informed the instance, so they change their behavior from enjoying fireworks to the evacuation behavior, right? And then, well, it's too small, but you see that some people carry question mark. That's our animation representing people who are not familiar with the area. Like today, I'm not very familiar with this building. If somebody asks me to evacuate, I have no idea. Should I go to the right, the left? Probably I will follow where crowd go. Or people who don't have any question, that means they are very familiar with the area. Those people who make decisions, right, that from this building, I'm sure that you go there, you go there, you go there, you have that idea. So I'm not going to spend much time, okay? I'm going to wrap up soon. But this is our model. Cave, virtual reality. So I will show you. So we have a cave, right? And then we conduct a lot of human experiment to understand their behavior, right? And then we develop, parameter for our BDI. By the way, belief, desire, intention is AI model. Okay, that people 1983, they are using those models for the atomic, robotic soccer. Right, their behavioral goal was optimum behavior, team behavior. Here is a human, a lot of errors, a lot of the perception. How about the learning? How about forgetting, right? So those actually a lot of emphasis that we put. And then we combine this environmental human behavior environment so that we need to have a lot of the environment so that I don't go through the walls and so on, right? So that we combine it and that give us the detailed emergency evacuation behavior. And then we have a very detailed model, and then I'm not going to go through, but we use a tool like a Bayesian belief network when we conduct a lot of the human experiment in cave. And then this is something called the decision field theory. I just mentioned this one for the decision theory. There is a prospective theory, right? Utility theory. There is a theory called the decision field theory. That's by Jerome Bussmeyer. He is very well known in mathematical, he called mathematical psychologist, right? So but his model is make a one-time decision. But in our view, when people make decisions, we don't make one decision. We always think, if I go there, if I go there, if I go there. So we extended this model for the multi-stage planning first, and then we follow the decisions, right? I'm gonna. This is Bayesian belief network, and then so one thing I want to show you is this is a cave. This is a Sung Ho Lee, the PhD now Samsung that his work discovery people came. This is a while ago, okay, when VR wasn't very popular, and then at that time we didn't have a unities and so on, so we used Google, something called the Google Sketches. It takes forever to develop realistic model. Okay, nowadays, right, instead of a cave, actually, Ramses and our team, we are waiting for the cave. Okay, and then so people we use all this headset, and then so the simulation that I want to show you nowadays, it's pretty cool, right? So the top one is this is a unity over. This is a model. This is a top view, crowd movement, and different street view or different angles and so on. By the way, this is the model developed by Unity that are displayed in cave, and human is in the middle. And we change a scenario. We keep asking, where would you go? Do you go to the right, the left, and then based on the data, we develop. So based on that, this is a decision field theory. Is again, I don't go through, but this is a model itself is very simple linear system. The key here is this simple model was demonstrate to represent human decision-making behavior under various scenarios. When people buy a car, when we don't have a time constraint, people think enough time, or you need to make a decision given time constraint, and then they are psychologists, right? So this, in the literature, this model is known to represent people with a behavior involving number of options. You can evaluate 2 car, 3 car, 4 car. Each car have a number of attributes: price, reputation, gas mileage, and so on, right? So that's actually the decision field theory. And I'm gonna just skip really the emergency evacuation model that you saw in Washington, D.C. It looks pretty simple behind the scene. It's very slow. Everybody, they go through this process. What they do is, you are here, And then let's assume that bombing attack occurred. This is your destination. And initially what you do is, instead of so you observe, should I go to the right, left, front, and back? And then virtual reality offline experiment, I developed Aldo's model, I developed Son's model, right? Ramsey's model, so that we actually provide the input that give us the different behavior model using the Bus-Meyer decision field theory. The output of this model is a choice probability of the selection. And then at this point, we needed to toss a coin, randomness of the simulation. So then, okay, you decide to go to here, but you are physically here. Your planning side, your thought is there. And then we needed to do the same thing. I'm physical here, or should I go to the up, down, here, and you do the same thing with a limited information. But Bayesian belief network is supposed to work with the limited information actually as well. So that's how we go through the planning side, and then I'm going to wrap up soon. So this is a lot of the open CV stuff that we cannot go to the park, we cannot go to the border outside often. So this is a very old model, but nowadays Unity resolution library gets better and better, so that a lot of algorithms that we use, like detection or OpenCV, we can use actually this video coming from the physics-based simulation as well. So a lot of our PhD students here, they play a lot with the Unities and game engine nowadays, right? So summary, I talk about some different use. I'm sure that, civil industrial engineering, many of you may have used part of this one, but I think this is really different, innovative use of the multi-paradigm simulation. I talk about system dynamic discrete agent-based model. Second one, digital twin simulation-based planning and control using model-driven architecture. All the system is automatically generated when you add and change the layout and so on. The third one, we extended this one to the higher level. So if a computation support, networking support, you can maintain your fidelity, or you need to aggregate. We use the system dynamic model. Once you do that, then you need to think about how do you synchronize higher level, lower level, the decisions and calibrations and so on. The last one is a really specialized agent-based model based on cognitive architecture that we developed, we extended, belief, desire, intention model. So that's my talk. Thank you for coming today. We have time for questions?
Oh, yeah, of course, yeah. So thank you so much for the interesting presentation. So the floor is open if you have any questions, please.
Yes.
Questions. We have heard a lot about simulations, about particularly behaviors, understanding behavior of humans. But I've noticed particularly people using Unity now, they use a lot they are creating engines or creating artificial intelligence that are very good at playing different video games. And they do it by doing what you're doing. They take the image and they study the different elements, and then they assign that there is soldier and it has different properties as a knife. And in the factory we'll have workers and we will have forklifts. So what they develop is an optimization strategy so that they can beat the game better. Now, do you think that would be something that we could apply here into optimizing the layout of factories and optimizing floor plans in order to basically get a better result of more efficient behavior when you're interfacing this let's say multiple types of soldiers, let's say workforce and forklifts or other sort of robots?
Rob, absolutely right. That we have a layout, the design software, so flow layout, cellular layout and functional layout, and so actually I have a paper on that. What that is so there is when you design, you talk about layout, design a building, depending on the factory, normal factory versus factory dealing with a hazardous material, the regulation is different. And so kinetic material, what is the minimum distance to axis should be shorter, the minimum width of the aisle should be wider, and so on. And what we did was exactly same production volume, number of the resources. We just evaluate different layout using productivity, so that one layout better than the other. We didn't change anything. We just set a fire. How does that affect the workers' evacuation? Completely different. So government standard organization still, right? They have a guideline and then rules, mostly based on this again static or performance. So that again, to answer your question is that yeah, people use discrete event simulation for the different layout, but human behavior, I mean, this is our behavior, but this is really the reason why I emphasize hardware in the loop, human in the loop is if someone has the best optimal behavior, we can, we can use using our web services, that behavior can be incorporated, and then we can use different type of the behavior, optimum behavior. But talking about these AIs and so on, that nowadays, right, next time, hopefully that I show we actually having this agent-based model with a lot of, we talk about the ChatGPT, many scenario cases that we don't have the data and so on, so that we are gonna, right, again, data can come from the statistical distribution, your historical data, or some other kind of the library or so on. Okay, so again, what I try to say is that we can, incorporate, integrate all these different to do the best, actually, the optimum layout or decision. Right? Okay. Yep. Yes.
First of all, I think it's really interesting that you take the aggregate data from the drone and also the ground group. I saw there was a diagram. You take real footage and the detection and the Unity simulation, and you compare that. I saw there's also an arrow going from the detection data going into feeding into the simulation. I'm wondering how does the footage data play into the simulation? Does it change the simulation at all? Do you use it as well?
Well, great question. So I talk probably a lot about this command actually side. Robot, for example, robot or UAV will be different. But robot, if we ask to do the same thing, variability will be very low, right? If they do the same thing, probably almost the same. But if that's a human or UAV, UGV with a different terrain, so that we can use as a lot of even data collection as well, right? So that your model, when you get this, a lot of the monitoring, your model continue to change. Distribution can change or it should change, right? Yes.
Thanks.
Thank you.
Yes.
So maybe we give right to ask the audience on that.
Okay.
So
I will
think
get back.
Julia has a hands on. Do you want to unmute yourself to ask question?
Julia. So what?
So and then if Julia is not there, then
You can ask them to type question actually as well.
Yeah.
And
there's
okay.
one more.
Obviously, I'm fine with the behavioral models that you put, but since you already have a simulator, let's take devil's advocate. Why not just use reinforcement learning to learn down the behavioral society?
Well, the goal here is reinforcement learning that, yes, I mean, that's we had a, fuzzy inferencing based reinforcement learning for the distributed control that we had that one long time ago using pure learning algorithms, right? And that's, again, optimal behavior. The human may not be optimal all the time. And what you didn't see, BBI, the middle is something called emotion module and learning. So now I learned West Lafayette a lot, but let's say somebody who came West Lafayette, you drive here, you drive there, so that you learning. So we have a paper on learning, how your model change learning. When I presented this one Air Force, they said, do your model forgetting? What do you mean? Well, pilot behavior, and so if they don't do their, the performance degrade, right? So that any the model here, like a Bayesian belief network. As you collect more data, how do you change your like a parameter? At some point, you forget one of the node will disappear. Structural learning actually stops, right? In order to address, basically we try to use this modern algorithm to construct the human behavior thing. Yeah. Somebody, yes.
Yes, thank you so much. I think I learned a lot, but just want to make sure I learned. The digital twin and the simulation based planning control. Give an example for the coverage problem. What's the coverage maximum?
Okay.
Right. So the fused data go into the simulations. Is that information is about the behavior of the human subjects or some subject that we're robots are looking at it. The end control is the command to the robot based on the simulation data. But how often do you actually does the fused information include the robots kind of localizations? Because let's think about just forcing, and there is some kind of disparity kind of accumulated based on the real application of how they do versus simulation. But you update the simulation?
Yeah, sure. So clarify. So the commands, I didn't mention the second one. What are the control commands?
Yes.
That's a waypoint series of the waypoints for how long. That needs to be our decision. But for each UAV, next planning horizon, I want you to go to the A, B's, and C's and D's. That's a control. And then a UGV is the same thing. Go to the waypoint. Okay, so that's a control part. And then based on the output, right? The kind of the change that you can make is I didn't show the modeling, but our UAV model is it's a grid-based model. So we look at if that's a statewide, right? The pure, so that we actually use a square grid, and then of the reason. Entire reason, and we use a 0 or 1 density. If the density gets higher enough, we determine that, there are some groups. So the goal of the UAV is detecting groups of the people. The goal of the UAV is detecting DRI, recognizing, identifying whether this is a cat or this is a human individual. Okay, so the higher model is, you can still run only higher level model, depending on, again, computation. Your model, this is a 23 miles of the area. How many UAV do you need to do that, right? So that you need to really aggregate. But based on the input that you get, based on the performance, you need to continue to use it to update your underlying model, or but we hoping that model is accurate enough. We just use that simulation model to do the simulation optimization. And then, right, so what I call it policy simulator. The policy means, again, we need to define heuristic. I want 2 UAVs get closer. I want to get 2 UAVs as explore as much, right? So those are the type of the policy that we want to, and then those policy is the one that are used by real UGVs and UAVs, right? Of course, again, computation is infinite, and then communication infinite. Why not? We just do everything, centralize everything, decisions, and so on, right? So that's what we are doing. Okay.
That's a very clear explanation. For me, my interest is more in the low-level control of the UAVs itself, low-level controls of the UGA itself, such that the simulation is actually for simulating my dynamics of the robot as well, because it's not going to be correct. But is there any feedback loop from the hardware localizations of it? To the simulator, then you're going to accumulate it.
That's right. That's absolutely. If you collect a lot of those data later, then you get it and you can develop exactly. That one again, UAVs are, as I said, our current one. I mean, our current is some people say that nowadays camera is better. So when I use it, I didn't show it, but it's a resolution of this camera is our assumption, which is true. If this is very high, it's not as good as resolution of this one. If this resolution is good, then why do you aggregate this, aggregate and so on? Okay. So right now the data that we get is model, the update, not individual model of the UAV, but we can if you have that data, we can use it for the develop. That's what we should, right? Yes. Yes.
I actually have a quick question. So since I've been working on digital twin in the concept of Unity since 2018, so actually I found this very interesting. But I'm working more on the autonomous ground vehicle now, UAV. But the question is, I mean, you talk about the digital twin for smart factory, digital twin for human behaviors. There is always a question that I got asked a lot of times is how accurate or how high fidelity is good enough to simulate all those for a digital twin, right? You can argue that those digital twins that are very high fidelity, they can simulate whatever is really happening in the real world, but it's not 100% true. There's still some error, there's some uncertainty of your digital twins that cannot simulate everything in the real world. And if you rely too much on digital twins, false decisions or false judgment might be made. So how accurate is accurate enough for digital twins?
Yeah, so your transportation actually the field. So you saw the transportation is a each and choose model. So that's a really I had a civil engineer, Federal Highway Administration project that he was a PI, I was a technical PI, and he want to use my BDI. So he has a his own meso level. They call it micro. You are expert, right? Meso level simulator of the Phoenix. Tucson to Phoenix network involving 2.5 million vehicles. So he's a meso level civil engineer, had a simulator. So what we did was, our conclusion was, we had our PVI model using web services. It's a 2.5 million, so 0.01%, only like handful people. We just send that scenario to my PVI model, make a decision, comes back. And then it also the Dynasty is the tool, right? Dynasty has its own human behavior model. That's very well known model, right? And then there are many scenarios that the human behavior model that Dynasty has match with our model is a lot more detailed. Therefore, it's not always good, right? It takes more time. Data may not be available. There are many scenarios that this model can represent our model. But there are many emerging cases, dynamic cases, right, that this model cannot actually represent, right? So I just answered this question with of course, depending on the scenario and situation, the level of the detail of the modeling. Also, if you don't have much data, right, that I have a factory, my factory, I didn't show, but that factory, I have a 3 level. I have a model for the individual machines. I have a model for the individual, the robot, and then yes, that's a hierarchy is a key here, right? That we need to select that. That's actually what I mean, right? So this is really the decision, right? The real factory decision. Factory decision to product. These are alternative. When I talk about alternative, this is alternative for each individual robot, each individual machine. This is the decision that needs to be made by, cell manager. This is the decision that needs to be made by shop manager. And then we have another level for the supply chain, the managers. And then what level we needed to go in, I thought I had a DEDAS, yeah, so what the DDS is really dynamic data driven adaptive simulation. So exactly depending on the urgency, the idea is if you are cell level manager, you just observe, right? You're not looking at robot in machine. You just look at cell level performance. If that's a plus and minus, then you don't need to go into the detail. But some area, something is out of the bound, then you still do not know whether that's so. What we do is we just go to our DDS simulation is instead of the entire factory has the same level, some area is very detailed, some area is a very high level. So that's actually, we call it DDDAS, Dynamic Data Driven Adaptive Multi Simulation Framework. Okay, so
So we have one question from the online audience. So,
So does
okay.
the simulation model consider scenarios in which certain agent find enjoyment in observing or recording bomb scenes in today's context? It's possible that many influencers might prioritize physical such situation over because they may inevitably. We really didn't do the formal experiment, so the answer is no. But right, that's a it's a again right. If people know that again we are not recording anything, right, and then so no, the answer is no. But I can use the another related question. So during the COVID, when I was in Arizona, that we developed the people movement model who comes to campus. We don't know exactly how many people come, but we have a lot of the Wi-Fi data in each location. We get the Wi-Fi data, and then when our university president open up, okay, this classroom, I don't know, capacity is like a 60 or 40, I mean 50. Would it be okay to open up 100%, or would it be okay 50%, 20%? That's an individual class model. This is a relatively small, but some big classroom has a 6, 7 different doors, right? So that again, I work with the campus health to simulate, right? Also social distancing simulation. Okay, so yes, we didn't do, but the reason why I mentioned about this, the human is that again, that model, we don't know exactly how many people, but we can use the Wi-Fi data to get aggregate number, and then we just populate the random, the people, and so hopefully that answer your question. I'm sure that behavior will be different if the people know, right? So, yeah.
So yeah, we have
Yes.
question.
I have a question to your human behavior model. Would you be able to share how you kind of made the evacuation condition for the humans? Like, what was it just distance to the bombing, for example? Just in case, for example, if you have multiple bombings in the city, what would be? Will they just get far or find shelter?
Yeah, that's this scenario, as I said, it was given by us, and I just showed the emergency evacuation simulation, but there is another university team to simulate the plume. There is another team developing metro. Okay, and then we use a distributed simulation because metro, some people coming out of metro or something, they go back, so we integrate. And then, so the goal of this integrated simulation was to support the decision of the law enforcement people. Okay, so the data that you didn't see, but a lot of graph on the right-hand side, how many casualty, what is the average time of evacuation for the experienced people, commuters, or tourists, okay? And then so the kind of the what if analysis we do is a value of information. At that time, mobile phone was still there, but what we do is no people share no information versus what is impact of the information sharing, right? And then another scenario is so their decision was, how should we deploy the policeman if there is a second attack, right? So those are the kind of the decisions that people use using our simulation. But that's a behavior here is really one of them is called the instinct, right? Instinct means I have no idea. So this we go through. This is very interesting, by the way. This decision behavior. When this got published ACM, so it's but the initial reviewer says that, how do you know that people go through those rational plannings and so on? People do. It can be very quick if we don't have any time. Something happened, I need to immediately, then I should go here or I should go here. But even evacuation now, right? I mean, people from the ECE, you need to go, you very quickly go through. Should I go here, there, and so on, right? So that's actually what we are, so if the time threshold is minimum, we have another behavior called we change from the decision to the instinct behavior. So you just follow your long-term memory in your technical term, long-term memory. You just follow your instinct, right? By the way, a lot of this one, we didn't make up. because there are expert psychologists and so on, so that we use a lot of the, but Jerome Bussmeyer, psychology, he's a very, very happy, right? The engineer use it and we use it again. We call it, we extended his one-time decision model to the multi-stage decision planning and then, decision control. He's Indiana University, by the way.
So I have one question related to the arena simulation of the military of the supply chain. So because like all the stakeholders in the chain, they want to protect their like business secrets, right? So how they exchange, like what kind of information they need to be exchanged, so it can be informed the other stakeholders in the chain,
Right.
to make another decision.
Right. So the what kind of information needs to be shared, what should be hidden, right? Just like the state chart or state machine, like a robot and machine. Robot pick and put, machine open door, start process, close door. Those are the type of the events that needs to be exchanged. Supply chain, we don't want to share our machining capability. We don't want to share how many machines we have. We don't want to share, but the order messages that given from one company to the other company, since we agree to collaborate, right, is order inventory control below this threshold. The event is generated and sent to the transporter. Transporter is sent, that message is sent to the other company so that, oh, you should be expected. We don't know when truck will arrive, but they know the truck is coming. As soon as truck comes, another message is, that message is based on formal correct. It's error free. It's all based on, again, the system engineering model based on system engineering model driven architecture, right? So those are the type of the events that needs to be shared, not much the detail capabilities and like data.
Yeah, because that is a big challenges or barriers of like using like a large scale of digital tree, because they want to protect their business secret. Yeah, but we have another question from online audience.
Can you discuss more about features that are easy to automate versus those that require human interaction? Human, as I said, Craig, human is, so with the demo that we had a lot of large company come, can human be part of your system? Of course, that's the answer. So is that, I mean, the example that I used was fully automated, but actually the Camellia will know the Arizona system, everything is automatic versus the air didn't go through, so the machine door doesn't open automatically. So what we do is, so Arena, the simulation, they send a message to us. So human needed to stay there, but I cannot do anything until supervisor, in this case simulator, tell me. I just wait, and then it asks me, oh, son, why don't you open the door? Then people physically open the door, and then I need to click button so that simulator knows, right? So that's a way that human actually can be. But that's, I just answered that human can be part of the system that are controlled actually here. But yeah, I mean this automation question is it's ROIs and safety and others, right? That again, the fully manual, fully automated, and we just had this discussion with our alumni who has a big battery, company, and then he talked about actually you share, right? Talk about this, ROI, right? There are areas that we cannot really justify ROI, okay, but there are areas that the return on investment of automation, can be, possible. We will have a lot of such kind of the discussion, Craig. But when we have AMR, autonomous mobile robot, if you look at the real, right, the distribution center and warehouse, really a lot of human robot collaboration, right? That just the robot comes in, everything is ready, human work is right. So but that really needs to be analyzed, greatest detail, right? Yeah.
Thank you so much. Any other question? So you for online audience, if you have any question, you can also email Professor Son, and for other, you are in the room, you can stay here because we observe, we reserve the room until like 5 p.m. So you can chat with the speaker. And please join me to thank you, our wonderful speaker today.
Thank you for coming. Let me know if you want to learn more or collaborate. Okay, so thank you.
Oh, thank you. Yeah.
I think maybe you need to cut the record because it's
Yeah,
in
yeah.
the discussion.